This video is about constructing a computer model for the motion of a spring mass system which oscillates as shown. The forces acting on the system are the force of gravity, which is a constant force, and the tension in the spring, Fs, which is a varying force. The force of gravity, Fg, is given by the product of the mass and the acceleration due to gravity. The spring force, Fs, is the product of Ks, the spring stiffness, and S, the extension of the spring. Fs varies since the length of the spring, and therefore the extension, S, is not constant during the motion. The motion of the mass will be influenced by the net force, Fnet, which is the sum of these two forces. Using Newton's second law, the new velocity Vf is given by Vf is equal to the sum of Vi plus Fnet delta t divided by m, delta t being the time interval and m the mass. We first analyzed the video in Tracker to extract position against time data in both the x and y directions as shown. If we consider 4 cycles, we see that the time taken is of 6.078 seconds, from which we can calculate the time for one cycle to be of 1.52 seconds. Then, using the equation t is equal to 2 pi square root of m divided by ks, we can calculate the value of ks to be of 6.87 Newton per meter. We next come to the Python codes for implementing the model. So here the model parameters are set at m equals 0.402 kg, while the value of ks is set at 6.87 Newton per meter. The next screenshot shows the calculation of Fnet and the implementation of Newton's second law. We now run the code to see the graphs observed and the motion of the pendulum. The ball in blue is the modeled motion, while the ball in red shows the actual position. As we can see, the model is not perfect, an imperfection further revealed in the graphs. Considering the graph for the y position, we see that there is a fairly good match between the actual data and the model. However, the time period for the x position does not match. If using the graph of x position from Tracker, we calculate the time period for the oscillations in the x direction, we get a value of 1.64 seconds. This implies that the value of Ks used is not appropriate for modeling the motion in the x direction. We now come to energy considerations in the system. So here we are showing the code lines used to calculate the change in the different energies involved. On the same axis, we plot the change in kinetic energy, the change in gravitational potential energy, the change in spring potential energy, and the total energy. From the graph we can conclude that the energy principle is satisfied, since the total energy given by the yellow line, which is the sum of these energies, is always a constant.